Hello there and welcome to the second lesson on thermodynamics. Today we're going to talk about ideal gases. Now, ideal gases are something that you probably heard about before. You may have learned about them in chemistry class. We're just going to build on what you would have talked about in those classes, and we're going to think about them from an energy and an energetics perspective. So the first thing you're going to know about gases that you learned a long time ago is that gases are these particles that are just freely bouncing around all over the place. So we say that gas particles are in constant random motion. And so we are going to talk about ideal gases. And it turns out that you just have to make four kind of simplifying assumptions. And then the way we treat our gases becomes much, much simpler. So this is actually a kind of a trick we use. And so when we deal with gases, we're going to assume that they are ideal gases. And what we do is we make four simplifying assumptions that make the calculations much, much simpler for us when it comes to how they behave. So the first thing to recognize, let's take a picture, let's take a look, say, at a gas sample. So you can see this container here. I've got some gas particles that are bouncing around. And the one I want you to notice is it's like as though we zoomed in on a little section of the air that you're breathing right now. Because if you look at the temperature, we're at 293 Kelvin, so that's right around room temperature. And this pressure gauge here, even though it's bouncing around, you can see it's kind of bouncing around 1 atmosphere. So what that means is, if you were to zoom in and look at the particles of the air you're breathing, they might look like this little sample right here. And the first thing you should probably notice is that they are very, very spread out. Most of the space that is occupied by this gas sample is actually just empty space. So there's two different kinds of particles there. There's the kind of the red ones and the blue ones, and they may be different sizes, like the blue ones are larger, but really it doesn't matter that the blue ones are larger because most of the space around them is empty space and isn't actually occupied by the volume. So the first two assumptions that we're going to make, well, we know really that gas particles are tiny, like tiny, compared to the amount of space that they occupy. And because the particles are so small relative to the space they're in, then the volume occupied by the particle itself is negligible. Now, what does that mean? What I mean by that is that even though particles themselves do have volume, they take up space. If I have a really small particle like, say, hydrogen, or a very, very large particle like, say, sulfur hexafluoride, even though sulfur hexafluoride is way more massive and takes up way more space than hydrogen does, it doesn't really matter because really it's surrounded by so much empty space, the size of the actual gas particle is irrelevant. Okay. Now, the next two things that we're going to, Now, the next two assumptions we're going to make are a little easier to see if I kind of add some more particles to kind of make this a little more fun. So you can see that as these particles bounce around and spread out all over the place, definitely one thing you notice is that the red particles don't behave exactly the same as the blue ones. Like the red ones are moving much more quickly, but just recognize that both of the particles, that whole sample is at the same temperature, which means the average kinetic energy of all these particles is the same. The blue ones are slower simply because they're more massive, but they do have the same kinetic energy as the red particles. So what you'll see here is that these particles are bouncing around all over the place, and when they reach each other, they collide. Now, we are going to make the assumption that the only interactions these particles experience are collisions. So they hit each other and they bounce off. In real life, you may have learned in chemistry that there are these things called intermolecular forces. And so when particles come near each other, they might actually attract and kind of stick to each other a little bit. And we're going to assume that those forces are, again, negligible. And the only interaction that's going to exist is going to be a collision. And that's the second thing about these collisions, that as they bounce around, we're going to assume that those collisions are perfectly elastic, which is to say there is absolutely no loss in kinetic energy. And so we'll make those two assumptions. The gas molecules interact only by collisions. So they can collide with each other, or they can collide with the walls of the container, but that's it. There's no like sticking together. There's no intermolecular forces. And the last assumption here is that the collisions between the molecules or between the sides of the container are going to be 100% elastic. And again, that means we're not losing any kinetic energy by that interaction. So once we make those assumptions, then we can start to think about, okay, so what is going to happen to these gas particles if we change some of the things about their surroundings? We could change the pressure, we could change the volume of the container they're in, or we could change the temperature. And so because gases can be compressed and expanded, they're going to react differently in each of these different situations. So that leads us to kind of three, let's say, precursor laws to an overall ideal gas law. So what I'm going to do is I'm going to keep the temperature constant, and I'm going to change the pressure and see what happens to the volume of this gas. So if I jump back to this sample here, say I've got this these particles bouncing around, I'm just going to lock in the temperature. So the temperature cannot change. What is going to happen to the pressure over here, for example, if I increase or decrease the size of the container? Well, we can see here that if I were to smush these particles closer together, but keep the temperature constant, my pressure is actually going to go up. And if I was to expand out the size of the container, again keeping temperature constant, the pressure goes down. And this should sort of make sense because the pressure is really just the sum of all the collisions of the particles with the sides of the container. The more collisions and the faster those collisions, the more pressure there is. Well, if I spread the particles out, even though they're moving at the same speed because of the temperature, there are going to be fewer collisions happening all the time. So you can see that pressure and volume have essentially an inverse relationship. So if I sketch a graph like this, it's going to look something like this, which is to say that pressure is proportional to the inverse of volume and vice versa. So if I increase the volume, pressure goes down, and if I decrease the volume, pressure goes up. Now I find it really helpful to kind of picture what's happening with these laws by thinking of an example. And one of the simplest examples that I can draw for you is to think about what's happening to a gas inside a piston. So imagine I've got a piston. This piston is free to move up or down. It can slide up or down. And what I'm going to do is I'm going to fill this piston with an ideal gas that's moving around, okay? And so it's bouncing around. Now, this gas must be under some amount of pressure. The piston must be pushed down. Otherwise, the lid would just blow off of this thing because of the gas itself bouncing around. And so the pressure, you could think of that as being like putting a little block, right? So putting a block of some mass on that piston, which is going to push down on the gas, and that's going to create a pressure which kind of keeps it in place. So what is going to happen to this little system here if I keep the temperature the exact same, but I increase my pressure? So what would that look like? Well, you could imagine increasing the pressure would mean loading more and more mass on top of the piston. If I load more and more mass on top of the piston, well, then that means that the piston is going to compress. And that's because I've held the temperature constant. So because the particles in here are at the same temperature, they still have the same amount of kinetic energy on average, they're not going to be able to support as much that greater pressure unless the particles are closer together. And so we can see here pretty clearly that if I increase pressure, so if pressure goes up, then volume has to go down. And that's like a pretty clear, I think, relationship. So let's look at this second one, which is sometimes called Charles's law. It's hard to say. So what happens if I keep the pressure constant? So in this case, what is going to happen to the volume and the temperature if I keep the pressure constant? So let me jump back over here to my example. So now I'm going to keep the pressure constant. And what I'm going to do is I'm going to change the temperature. So the pressure has to stay the same, but I'm going to increase the temperature. And you can see that as I increase the temperature, those particles start moving faster. If I'm going to keep the pressure felt by the sides of the container the same, well then those particles are going to have to take up more space. And the same thing is true if I start to decrease the temperature. So if I cool these particles down, they are going to occupy less and less space in order to keep the pressure the same. That is to say that because they're slowing down, they're colliding with the sides of the container less and less, which means they must be closer, packed closer together in order to provide the same pressure to the outside. So that means that this relationship is going to look like this, that I'm going to have kind of some sort of direct relationship, that the volume is proportional to the temperature. If I increase the temperature, I increase the volume, and if I decrease the temperature, I decrease the volume, and so on. So what would this look like in our little piston example? Well, if I'm going to have a piston and I have some amount of pressure because I place mass on the piston, these particles are happily bouncing around, okay? But what happens now if I heat them up? So I'm gonna add heat. I'm gonna put a flame under this thing. Well, those particles are gonna move around even more and more quickly. If I don't put any more mass on this piston, if I don't increase the pressure, well, then the piston is going to rise, right? It's going to rise up in the air, which as a result means I'm going to increase the volume of the container I'm in. And that's simply because these particles are now moving around much more quickly. And so they can cover more space and still provide the same amount of pressure. So you can see here that as the temperature increases, so does the volume, right? Temperature goes up, volume goes up. And the last one, sometimes called the Gay-Lussac law, which is what happens if I keep my volume constant and then change the temperature and pressure. So again, I'll jump back over here. Now I'm going to keep my volume constant, and you can probably get an idea of what's going to happen here. So if I keep this container rigid, I'm not going to allow it to expand or contract. If I add heat to this, these particles are going to move around more and more quickly, which means they're going to collide with the sides of the container even more and more often, which means the pressure is going to increase. And you can see the opposite is also true. If I cool things back down, the particles slow down, there are fewer collisions every second, which means I'm going to have less pressure on the sides of the container. So this law is also kind of similar to the last one, which is to say that if I plot pressure versus temperature, it is a direct relationship, that the pressure is proportional to the temperature. And we can picture this like a piston, okay? So imagine, again, I've got a piston and it's sitting because I've got a mass sitting on it. And so the particles are just kind of bouncing around and keeping that mass suspended in the air. But if I add heat, if I put it under a fire and I add heat, if I don't want that piston to rise, if I want it to stay in the same spot, I'm going to have to add more weight on top. So I'm going to have to take this same piston and I'm going to have to pack a whole bunch of weight on top of this thing. Otherwise, the piston is going to rise. So if I want to keep the volume fixed. And that's because those particles are moving more and more quickly, and there's more and more collisions happening all the time. So you can see that as the temperature went up, then so did the pressure. Okay? So all three of these laws kind of all combine together into something overall called the ideal gas law. And we're going to see in later units that sometimes we might do this experiment we just did here. We might keep the pressure constant or the temperature constant or the volume constant and think about what happens. But for now, we can take all of these relationships and put them all together into one ideal gas law. So the ideal gas law kind of comes in two forms. It just depends on which textbook you're reading. You'll see it in one of two ways. Basically, it says that P times V is equal to NRT. Now, I just want you to take a look at this for a second and just recognize that this is saying the same thing we said before. Pressure is directly related to temperature. Volume is directly related to temperature. Because volume and pressure are on the same side, they must be inversely related to each other. So these symbols here, we know most of these, but we'll just write them out. So this is our pressure, okay? So that's pressure. And note that pressure has to be in pascals. Otherwise, this is not going to work out. And then, of course, V is volume. And volume has to be in cubic meters, not liters, okay? N is the number of moles. So obviously, if I have more particles of gas, like we saw in that simulation, then that's gonna create more pressure or take up more space, whatever have you. If you haven't learned about moles before, you might want to know, well, you might know that 1 mole is equal to 6.02 times 10 to the 23 particles. Okay, so it's a way we measure really small things like atoms and particles, and 1 mole is really just a lot of those particles. And R is just a constant. So R is the ideal gas law constant. And it has a value of about 8.31 joules per mole Kelvin. And then, of course, last but not least, here T, I've got temperature. And we need to make sure we measure our temperature in Kelvin, K. Now, the other version of this law that you might see, it looks very, very similar, but we just kind of switch out the constants. It just looks like this. It's just PV equals big N KB times T. And you can see that the variables are all the same. All that changes here is whether we're going to talk about moles or whether we're going to talk about particles. So N here would just be the number of particles. And Kb is just a different constant called the Boltzmann's constant. And it has a value of about 1.38 times 10 to the negative 23, and that is measured in joules per Kelvin. Okay, so just a couple things that follow from this ideal gas law. The first thing to recognize is that we talked about this already, that the pressure inside a container really is caused by all these particles bouncing around. And so the pressure is really just the result of the particle colliding with the wall of the container and experiencing a force action reaction pair. Okay, so particle hits the wall, wall hits the particle. And so from the ideal gas law, PV equals nRT, since the pressure is related to the force of those interactions, and the force is also related to how fast those particles are moving, which is related to the temperature, we can go through a big complicated rigmarole to basically find the average kinetic energy. So the kinetic energy average of the particles in an ideal gas is equal to 3/2 kb times T. And so again, this K average here, this is just the average kinetic energy. And Kb is that Boltzmann's constant that we saw on the previous page. The key thing to take from this here, the really key insight, is to just recognize that the kinetic energy is proportional to the temperature. And we've been talking about this already, but it's sort of right there in the math, that the average kinetic energy of these particles bouncing around is just related to the temperature. If you double the temperature, you double their kinetic energy, and so on. So this really provides an explanation of why it is that the particles making up a substance move faster when the temperature is increased, because that temperature is related to the kinetic energy. And so you could calculate the average speed of these particles if you wanted to. You'd have to use the fact that the kinetic energy is equal to 1/2 mv squared, and we now know that's equal to 3/2 kbt. But long story short, you could find the velocity, and that would equal the square root of 3 kb times t all divided by m. But I just want to point out here that this velocity here, this velocity is an average, and it's called the RMS velocity, which stands for the root mean squared velocity. And I'm not going to get too far down the rabbit hole of what that means, but just really understand that that's just a way of taking the average. It turns out there's a few different ways of taking the average of a velocity like this, but this is called the root mean squared. And so you can see that the root mean squared, or the average velocity of the particles, is really just going to depend on the temperature and the mass of the particles, which, if you think back to that simulation, the larger particles just moved a little bit slower because they were more massive. Okay, so let's do a few calculations and then we're on our way. We've got a balloon filled with 1 mole of air at STP. Now, STP is something called standard temperature and pressure. And so standard temperature and pressure is defined as being at exactly 1 atmosphere. And 1 atmosphere is just regular air pressure, which is 1.01 times 10 to the 5 pascals. And it's also defined at a temperature of 0 Celsius, which is the same as 273 or thereabouts Kelvin. So how much volume will this gas occupy? Okay, well, we've got our fancy new formula, PV equals nRT. So we can solve this for volume and say that the volume is going to equal nRT divided by P. So plugging in our values here, I've got exactly 1 mole, isn't that handy? 8.31 for my constant, and then my temperature of 273, and then I divide by a pressure of 1.01 times 10 to the 5 pascals. And this whole thing, when I crunch the numbers through, comes out as 0.0224. Now remember that I'm finding the volume, and so the volume is measured in cubic meters. Now that number might seem kind of familiar to some of you, because if you were to convert that into liters, if I move that decimal place over 3 spaces, I would find that that is equal to 22.4 liters. And so You may have run across that in previous chemistry classes, and you know that 1 mole of ideal gas occupies 22.4 liters of space at so-called STP. But what if we change things about it? We change the pressure and we change the temperature. So for example, we take this balloon and we somehow submerge it in a pool, don't ask how, and we put it 2 meters deep. So now because it's underwater, it's gonna be under a lot more pressure than it was before. And then in addition to that, the water temperature is about 15 degrees Celsius. So that ends up being about, about 288 Kelvin. And so that's gonna heat up just a little bit. So what's the new volume occupied by this gas? Okay, so I've got, the first thing to recognize is that I'm now submerged underwater. And when we're underwater, the new pressure is going to be the air pressure P naught plus rho GH due to the pressure of the surrounding water. So this is going to be my original 1.01 times 10 to the 5 kilopascals plus the density of water, which is 1,000 times 9.8 times the depth of 2 meters. And so I get right around 1.206 times 10 to the 5 pascals. And so you can see that because of the depth of the water, our pressures increase a little bit. So I'll do the same calculation as before. I know that my volume is just going to equal nRT divided by P. And so we've still got 1 mole and then still the same constant, 8.31. And then I've got now a new temperature, so a little bit warmer, 288, but I've also got a higher pressure, 1.206 times 10 to the 5. And this whole thing is going to work out to be similar, but a little different, 0.0205 cubic meters. So you can see that the overall, the pressure made it compact and the temperature tried to expand it, but overall it was a little bit smaller. And then the last question is, what is the average kinetic energy of the particles of a nitrogen molecule in the balloon? Well, we know that the average kinetic energy is equal to 3 halves kb times the temperature T. So that's 3 halves times 1.38 times 10 to the negative 23 times the temperature, and we'll use the new temperature because of the water. And so that's 288, which gives us right around 6.2 times 10 to the negative 21 joules, which, not a big surprise, the kinetic energy of a single nitrogen molecule is really not that much. Okay, that is it for our lesson on the ideal gases.